Okay, everybody, this is my very first video, as it were. Now, I've promised myself I wouldn't do this, but I feel compelled to answer some basic questions from flat earth people to help them understand a bit about what's going on around them. Now, one of the questions that keeps coming up, especially from the lot in Scotland, especially that guy in the shed, is how come a vacuum can exist alongside a pressurized atmosphere without a container? And to add to that, this fella keeps asking for a demonstration of this. Okay. Well, demonstration's probably not possible. However, if he's got enough sense, he should be able to follow this quite well. First of all, at ground level, so let's say at sea level, the pressure is around about 101.3 kilopascals, and that's approximately 10 to the 25 molecules per cubic meter. That's about the concentration of molecules in every cubic meter at this level. Now, as you get higher and higher, you gain more and more altitude. In fact, this concentration gets less and less. Now, how do we know this? Well, a climber, for instance, Mount Everest, would need to take air, compressed air, to the summit. And the reason that he or she would need to do that is because there just isn't enough of it at 29,000 feet. And more than that, if they're boiling water, which they do at that altitude, the water boils at 70 degrees C, which is quite predictable. Because if you follow the formula PV over T equals P2V2 over T2, which is commonly used for diving or whatever, you'll find that that's quite accurate. About 70 degrees C, water will boil. In fact, right here, at 101.3 kilopascals, I can actually get water to boil without any heat at all. So all I need to do is, in a flask, use a decent vacuum to remove the molecules of air, and the water that's in that flask will boil. Okay, now, as I was saying, the molecules get less and less as you get higher and higher. If you go up to 40,000 feet, where an aircraft would typically cruise at, there's even less. This is sort of minus 51 degrees C. That's how cold it is. And very, very few molecules per cubic meter compared to what it was at 101.3 kilopascals. Further up, it gets less and less, and keeps going on like that until there's practically none. In fact, when you get about as high up as the geostationary orbit, so around about 36,000 kilometers, then the concentration of molecules per cubic meter is only about 100, which is really, really small compared to what it is on Earth. And not only that, as we observe these distances from the ground upon Earth all the way up to the 36,000 kilometer range, we notice that it happens gradually. It happens in a gradient. So we call this area a vacuum, and we call it a vacuum simply because it's an area that's lacking in molecules and gases. However, even those 100 or so molecules of gas do have some tiny effect on the equipment that's up there, particularly geostationary satellites. So there is some drag, but it's minimal, and we can account for that. So let's get back to this barrier now. You see, as I've described it to you, all of this gradient, right from the sea level all the way up to 36,000 kilometers, simply a lot of atmosphere to nothing practically. Why on earth do I need a barrier? What have I got a barrier for? What would a barrier do? Okay, so that must be pretty obvious to you now, yeah? I mean, you can't be a total idiot. Is that possible? So that now that you have got it, can I ask you please, flatties, to remove that question from your flat earth repertoire? Thank you. Next time I'll deal with another question.